Hello class. Okay, so yesterday we talked about the redshift and blue shifted, meaning that some stars were heading towards us, some stars are heading away from us. So what does that mean in terms of the Big Bang? If some are heading towards us and some are heading away from us? If there was a Big Bang, shouldn't everything be moving away from each other? Well, yes, it is. On the whole, if you look at the larger picture. If you can imagine, if I had a big jar of marbles and I just dropped all the marbles right to here. Okay, at first when they're still kind of close together and certain marbles are going this way, certain marbles might actually come close to each other or might be headed towards each other, but then they're going to pass and then move apart. So at first you have all these, so many different directions that things may appear to actually be moving towards each other, but really they were going to pass, and then on the whole everything's being spread out. Okay, hopefully that kind of gives you a better picture of what we mean by the redshift and the blue shifted. But on a whole, what we see on the average is that every galaxy is moving away from every other galaxy on the average. So if we had like a picture like this, okay, so say this is our galaxy, and we have actually observed all this and measured all this, and so say this is the Milky Way galaxy here. These are all the neighboring galaxies. Okay, so on average they're, the closest ones to us, but they all are moving away at some velocity. Okay, all the ones within this kind of radius here all are moving away from us in general with particularly the same velocity. Then if we look beyond those into the next set of galaxies, these here, we notice something strange. Okay, say if this galaxy was 1 light year away from us. There is no galaxy 1 light year away from us, just to keep the idea simple. Say if this galaxy is 1 light year away from us. This galaxy is 2 light years away from us. There's double the distance. But there's something strange about the velocity. Whatever this velocity here is, this velocity is double that velocity. So it's double the distance, but it's double the velocity. Okay, so what that means is that this one is moving away from this one faster than this galaxy is moving away from us. Okay, if they were moving at the same speed, then everything would kind of look kind of static and these would just kind of stay together. But this one's moving away faster than this one's moving away, if that makes sense. Okay, I have a video to kind of help explain that a little bit. But then something else we found, so that was in reference to us. Well, what about if we picked a reference frame of another galaxy? What would that look like? Well, no matter what galaxy we picked, we kind of see the same thing. Okay, those galaxies that are twice the distance are moving twice the speed, and even further out. If they're 3 times the distance, they're moving 3 times the speed. Okay, 3 times the distance, 2 times the distance, and the distance. And we see that constantly as further and further out we look. So the farther away they are, the faster their velocities are. That's kind of like those marbles. If you drop that ball of marble, you'll notice you have a big clump here, but then you got some on the outskirts that are just flying away from you, like going off the edge of the table. And that's kind of what we see. Those that are the furthest on the outside are moving faster than those that are on the inside. And so that kind of gave physicists a rather simple idea of that. Well, if everything's expanding this way, it's just like in a movie. If you saw an explosion, what if you could pause it and rewind it? It would go back to a certain point. So if everything is moving away, then you can basically replay it in reverse, and you can actually come to the conclusion that everything had to be at one point. That it didn't at the time, other than Edwin Hubble's redshift and blue shifted, that's all the evidence they had to support that theory. That was in the 1920s. Obviously, over the next 80 to 100 years, we've gotten a lot more evidence. And one of those pieces of evidence that we're going to look at next is called the cosmic microwave background. Maybe some of you have heard of it. The new image of the CMB was taken rather recently, a couple years ago, I believe. So we have a really good detailed idea of that, and that was one of the biggest modern day supports of the Big Bang. Okay. And also there's the idea of inflation, which we'll get into that a little bit next week. So I got a video to kind of show you what inflation is. So when we start talking about it, you might have a little bit better idea of it. But your assignment for this weekend, it will be due Monday actually, so not today, you have all weekend to do it, is write a half a page paper, typed, 12 font, New Times Roman, single spaced. Okay, so basically just 2 big paragraphs. Describe what the cosmic microwave background radiation is. Not what we're using it for, but what is it in general. How does that support the idea of the Big Bang? How far back in time does the CMB take us? When you start researching this, hopefully this will make a little bit more sense as you start reading. What do I mean by how far back in time does it take us? And then once you find out how far back in time it takes us, why does it stop at that particular moment? Like, it's kind of a weird random value it seems, but there's a reason for it. So explain that. Why does it stop at that particular point? Okay, if you have any questions about this, just message me on Teams. Thanks guys, have a good weekend.